Welcome back to the Quarterly Call. All content is for informational purposes and is not investment advice. Please consult with an investment professional. So, imagine a massive industrial complex that spans acres.
Right, taking up huge amounts of space.
Exactly. And it consumes enough raw electricity to power a mid-sized city. But when you look closely, there are no smokestacks.
No assembly lines either.
None. No conveyor belts, and absolutely no physical products leaving the loading dock. The only output of this colossal facility is, well, an endless, invisible stream of digital tokens.
Tokens that, honestly, over the next decade, are going to fundamentally replace the entire software industry as we know it.
Yeah, which is wild to think about. So today our mission is to unpack a massive paradigm shift in computing. We're doing a deep dive into a major 2026 tech presentation from the CEO of a leading accelerated computing company.
And it essentially outlines the exact architecture of this new world.
It really does. So whether you are a developer, a business strategist, or just someone trying to understand where the economy is moving, this lays out the blueprint for the next 10 years.
The central thesis of the presentation we're analyzing today is that we have definitively crossed a historical threshold.
Like a point of no return.
Exactly. For the entirety of modern computing, our relationship with machines has been retrieval-based. You input a command, the computer queries a storage drive, and it retrieves a static file.
Right. You ask for a document, it finds the document.
Exactly. But that era is over. We've moved entirely into generative computing. The machines are no longer fetching things. They are generating raw intelligence in real time.
Which means they're functioning as autonomous agents.
Right. And as we'll get into later, serving as the actual brains for physical robots navigating the real world.
I want to start right at the bedrock of how we even arrived at a place where a machine can generate intelligence.
Yeah.
Because the presentation dedicated a significant amount of time to historical context.
Yeah, specifically a 20-year hardware and software gamble.
Right, on a computing architecture called CUD. And looking at the math and the timeline they laid out, this wasn't just like a technical evolution. It was essentially a massive Trojan horse strategy, wasn't it?
Trojan horse is actually the perfect way to describe it. To understand the gravity of CUD, you have to look at the limitations of traditional microprocessors.
The ones that have been in our computers for decades.
Right. For decades, the standard paradigm was sequential processing. A processor takes one instruction, executes it, takes the next, executes it.
Doing everything one by one.
Exactly. It's incredibly fast at doing one thing at a time. But as we hit the physical limits of how fast we could run those cycles without, literally melting the silicon.
Which is a real problem.
A huge problem. The industry realized we needed to process things in parallel, meaning doing thousands of mathematical operations simultaneously.
Which is incredibly difficult from a software engineering standpoint, right? I mean, trying to write code that splits a complex problem into 1,000 tiny pieces.
And computes them all at the exact same time.
Yeah, and then stitches the answer back together without the whole thing crashing. It's a nightmare.
It was. Before CUD, parallel programming was basically a dark art. It was restricted to specialized supercomputers in, academic basements.
So what did this company do differently?
What they did 2 decades ago was build a software layer, CUDA, that allowed everyday programmers using standard languages like C++ to easily write parallel code.
Oh, wow. So they democratized it.
They did. But the brilliant part was the distribution mechanism. They didn't try to sell million-dollar supercomputers to start.
Right. They baked this advanced parallel computing architecture directly into consumer graphics cards.
Exactly. The presentation actually joked about this, pointing out that millions of parents buying high-end gaming rigs for their kids.
So they could play visually stunning video games, yeah.
Right. Those parents were unwittingly funding the foundational infrastructure of the modern AI revolution.
Because rendering a 3D video game, calculating millions of individual pixels on a screen simultaneously, happens to require the exact same parallel mathematics needed to train a neural network.
That's the Trojan horse. That gaming revenue subsidized billions of dollars in enterprise research and development.
And by putting this architecture in millions of consumer desktops, they created the ultimate flywheel.
A massive flywheel. When you have an install base of hundreds of millions of identical computing environments globally, you instantly attract developers.
Because the developers didn't have to buy a supercomputer. They already had one sitting on their desk in their gaming PC.
Exactly. They started experimenting. And that frictionless experimentation led to new algorithmic breakthroughs in deep learning.
Which then proved commercially viable.
Right, which birthed entirely new corporate markets, which in turn drove the company to build larger enterprise-grade data center systems.
So the flywheel spun faster and faster, locking the entire industry into their specific architecture.
Yeah, it's a textbook platform monopoly strategy.
But a flywheel that massive requires an immense amount of fuel to maintain its momentum. And in this context, that fuel is data, right?
Absolutely. Data is the raw material.
The presentation introduced two foundational software libraries designed to feed this massive computing engine, QDF and QVS.
Right, and on the surface, they sound like dry, highly technical IT upgrades.
Totally. But the mechanical implications for global business are staggering. Let's break down QDF first, which deals with structured data.
Structured data is the organized ground truth of human commerce. It's the massive SQL databases, the multi-million row spreadsheets, the financial ledgers.
The stuff that exists neatly in rows and columns.
Exactly. Historically, analyzing a spreadsheet with 1 billion rows using a traditional sequential processor creates a massive memory bottleneck.
Because the processor has to read a chunk, move it to memory, calculate it, write it back, and fetch the next chunk.
Right, it's constantly shuffling data back and forth.
Yeah.
QDF is a library designed to bypass that bottleneck entirely using accelerated parallel computing.
Meaning it allows a system to ingest and analyze titanic data sets simultaneously.
Yes, which is incredibly powerful for financial institutions or logistics companies.
But the presentation dropped a statistic that completely changes the context of this. They said roughly 90% of the data generated by humanity every single year is unstructured.
90%. It's a huge number.
We're talking about text-heavy PDFs, corporate emails, recorded video calls, long-form audio speeches, raw sensor data.
And until very recently, that 90% was essentially invisible to a computer.
Invisible because a traditional computer only understands binary storage, not semantic meaning, right?
Exactly. If you save a 1,000-page legal contract on a standard hard drive, the computer knows the file size.
And the date it was created.
Right, but it has zero understanding of the actual text. You could run a basic keyword search, but if you asked the database, does this contract contain any clauses that present a liability risk under European privacy law?
A traditional system would just freeze. It can't comprehend abstract concepts like liability or risk.
It's impossible for it. This is where the QVS library fundamentally alters the landscape. QVS handles vector stores and semantic data.
I want to make sure we clearly explain the mechanics of a vector store, because it's the core engine of how AI actually, reads.
Yeah, it's crucial to understand this.
When an AI system ingests an unstructured PDF using these accelerated libraries, it isn't just taking a picture of the words, it's converting human language into advanced mathematics.
Right, plotting the semantic meaning of every single word, sentence, and paragraph onto a massive multidimensional graph.
And that mapping process is called an embedding, right?
Yes, an embedding. Imagine a mathematical space with tens of thousands of dimensions. When the AI reads the word liability, it assigns it a specific coordinate in that massive space.
And when it reads the word risk, it assigns that another coordinate.
Exactly. And because those concepts are semantically related in human language, their mathematical coordinates are placed physically close together in this multidimensional space.
So the QVS library allows an enterprise to take petabytes of unstructured data, every email, every video transcript, every PDF, and convert it all into this mapped vector space at blistering speeds.
Blistering speeds! It's real-time comprehension.
I was trying to visualize the real-world impact of this, and here's an analogy that helped me grasp the scale.
Let's hear it.
Think of a massive legacy corporation's data architecture, like an endless, disorganized attic.
Okay, I like that.
For 50 years, employees have just been throwing cardboard boxes of files up there and shutting the door. You know the history of the companies up there, but finding a specific insight is functionally impossible.
It would take a human lifetime to read it all.
Exactly. What QDF and QVS do is turn the AI into a hyper-intelligent, immortal archivist.
An archivist that never sleeps.
Right. It can instantly read every single diary, analyze the lighting in every loose photograph, grasp the emotional anxiety hidden in a decades-old internal memo.
Mathematically plot all of it.
Yes, and hand you the exact operational insight you need the millisecond you ask a question.
The operational efficiency gained from deploying that archivist is difficult to overstate. The presentation highlighted a specific use case with Nestle.
Oh, the supply chain example. That was fascinating.
Nestle operates an unbelievably complex global supply chain. They make thousands of micro decisions daily based on data pulling from 185 different countries.
So you have structured supply chain data clashing with unstructured local regulatory documents and weather reports.
Right. And running that massive blended data workload on legacy hardware meant they were severely bottlenecked.
They could only afford the time and compute power to refresh their global logistics models a few times a day, right?
Exactly.
Yeah.
If a crisis happened in a shipping lane, they wouldn't mathematically see the ripple effects for hours.
Which is an eternity in global shipping. So
Yeah.
what happened when they switched?
By transitioning their data operations to utilize accelerated computing libraries, Nestle reported they are now running those exact same Titanic workloads 5 times faster.
5 times faster is a huge jump.
It is, but the critical metric here isn't just the speed. They're executing it at an 83% lower cost.
83%. Wow.
The combination of exponential speed increases and massive cost deflation changes the fundamental economics of how a company processes its own reality.
Which naturally leads to the next massive leap. Because once you've mathematically categorized all of the world's structured and unstructured data, and the AI can perfectly understand the context of your entire business.
That data is no longer just sitting idle in a server.
Exactly. The AI transitions from understanding to acting. The presentation called this the Inference Inflection.
The Inference Inflection, yes. And the numbers they laid out to prove this shift are, frankly, staggering.
They really are. How do they define this inflection point?
They framed the evolution of AI in distinct phases. The first phase was perception. The AI learning to read the data, recognize images, and understand human speech.
Right, like voice assistants and image tagging.
Exactly. The second phase was generation. The AI learning to write text, paint images, or synthesize voices based on prompts.
The whole generative AI boom we've been living through.
Right. The third phase, which we have been in recently, is reasoning. Giving the AI a complex logic puzzle and having it break the problem down into sequential steps before answering.
But the fourth phase, the inflection point we are crossing right now, is action.
Action. The AI isn't just reasoning about a problem in a sandbox anymore. It is executing workflows.
So it's actually doing the work.
Yes. It is writing a piece of code, testing it, finding the bug, rewriting the code, and deploying it to a live server without human intervention.
And because of this shift to active, doing AI, the presentation stated that global computing demand has increased 10,000 times over the last 24 hours. Wait, no, sorry, over the last 2 years.
10,000 times in 2 years, yeah.
10,000 times. That's insane.
A 10,000-fold increase in demand breaks every traditional forecasting model in the tech sector.
How does the industry even prepare for that?
Well, the financial reality of that demand is what the speaker pointed to next. They see at least $1 trillion in high-confidence infrastructure spending required through the year 2027.
$1 trillion.
Just to build the physical systems capable of meeting this compute load.
And this is where the language in the presentation took a fascinating, almost jarring turn. They were very specific in stating that this $1 trillion is not being spent to build more data centers.
Right. They insisted that the era of the data center is dead.
Which is a bold claim.
Yeah.
And they said we are now in the era of building token factories.
I have to admit, when I heard that terminology, it felt a bit, I don't know, overly industrial.
It does sound heavy.
Isn't a token factory just a marketing buzzword for a really clean, heavily air-conditioned warehouse full of expensive servers? Why lean so heavily into the manufacturing language?
The manufacturing terminology is vital because it reorients how business leaders must think about the fundamental product of the modern economy.
Okay, unpack that for me. A standard data center is essentially a digital parking garage. You pay to park your files there, and you retrieve them when you need them. The business model is based on storage capacity and network bandwidth.
Right, the retrieval era we talked about earlier.
Exactly. A factory, however, takes raw materials, applies energy, and manufactures a newly synthesized commodity.
Okay, see where this is going.
In this new architecture, the raw material is data, the energy is electricity, and the newly manufactured global commodity is the AI token.
So you're saying a token, which is just a digital fragment of generated intelligence, is now a tangible economic unit.
Yes. No different than a barrel of oil, an ounce of gold, or a kilowatt of electricity.
That is a wild paradigm shift.
That is, if you're operating one of these new facilities, your entire revenue model is based on the continuous, unbroken generation and sale of these tokens.
But why the strict factory metaphor? Why not just call it a token center?
Because factories are brutally bound by the laws of physics, specifically thermodynamics and electrical grid capacity. The presentation made a chilling point for anyone trying to compete in this space.
What was it?
A 1 gigawatt facility is permanently a 1 gigawatt facility.
Let's pause on that, because a gigawatt of power is an astronomical amount of electricity. That is roughly the output of a nuclear reactor.
It's massive.
Are you saying that once a company secures a gigawatt from the regional power grid, they hit a hard physical ceiling? They can't just call the utility company and write a larger check to get more juice if demand spikes.
The power grid simply does not have the transmission infrastructure to negotiate like that. You are physically capped by the copper wires feeding the building.
Wow.
You have 1 gigawatt. That is your absolute limit. Therefore, your company's financial survival is mathematically tied to a single overriding metric.
Tokens per watt.
Exactly. Tokens per watt. If you and your competitor both have a 1 gigawatt factory, but your competitor's hardware architecture can generate 10 times the number of tokens using that exact same gigawatt of electricity.
Your competitor will economically destroy you.
They will. They'll offer a faster, smarter, cheaper service, and your $40 billion infrastructure investment instantly becomes a stranded asset.
That is a terrifying proposition for a chief technology officer. If your total power input is locked by the physical constraints of the grid, and you can't magically summon more electricity, the only way to multiply your factory's output is to radically reinvent the hardware that consumes that electricity.
You have to squeeze more intelligence out of every single electron.
Which brings us to the third major theme of the analysis, the hardware revolution, and a concept the presentation referred to as extreme co-design.
The engineering leaps discussed here border on the unbelievable, frankly.
They really do. Where did they start?
They established the baseline by looking at the recent generational jumps in their supercomputing platforms. The Hopper architecture, which essentially ignited the massive public generative AI boom, was the starting point.
Right, that was the big catalyst.
Then they moved to the Grace-Blackwell architecture, which they stated delivered a 35 times increase in performance per watt over Hopper.
A 35 times leap in a single generation is absurd. I know we have to look at these corporate claims analytically, but the presentation even pointed out that an independent financial analyst accused them of purposely sandbagging that number.
Right, suggesting the actual architectural leap was closer to 50 times.
Whether it's 35 or 50, the efficiency curve is just going vertical.
Yet Hopper and Grace-Blackwell were just the prologue. The centerpiece of the hardware discussion was the full unveiling of their brand new platform, Vera Rubin.
I spent a lot of time looking at the mechanical specs of the Vera Rubin system, and it challenges standard computing logic. We're looking at a single, cohesive system capable of 3.6 exaflops of compute.
And to put that in perspective, an exaflop is a billion calculations per second.
It's unfathomable. It utilizes an architecture called NVLink 72, which essentially wires dozens of massive processors together so tightly that they act as one giant unified brain.
A single massive computing entity.
But the detail that fascinated me the most was the thermal management. The presentation proudly declared that Vera Rubin is entirely liquid-cooled.
Yes, no more giant fans.
They showed images of the racks, pointing out that the traditional massive bundles of thick copper networking cables are completely gone, replaced by complex hot water cooling systems flowing directly over the chips.
The transition away from traditional air cooling and copper wiring is basically a forced hand by the laws of thermodynamics.
Because it just gets too hot.
Right. When you cram 3.6 exaflops of compute into a physical rack, the thermal density, the sheer amount of heat radiating off the silicon, surpasses the capacity of moving air to cool it down.
Because standard fans would literally be blowing hot air onto hotter chips.
Exactly. Liquid is exponentially more efficient at transferring heat. And the removal of the copper wiring is equally critical due to signal degradation.
Right. If you're moving data at exabyte speeds, the electrical resistance in a physical copper wire actually slows the signal down, right?
Yes, and it generates even more heat in the process.
It's a vicious cycle.
The physics basically demand optical connections and direct-to-chip liquid cooling. But alongside the thermal engineering, they highlighted a brand new central processor designed specifically for the Vera Rubin platform.
Utilizing highly specialized LPDDR5 memory.
Right, and the reasoning behind this specific memory choice goes back to the shift from generative AI to active agentic AI.
I was wondering about that. How does an autonomous agent change the physical memory requirements of a processor?
Yeah.
Why couldn't they just use standard high-bandwidth data center memory?
It comes down to the rhythm of how the machine thinks.
Rhythm.
Yeah, when you're training a massive AI model, you want sustained ultra-wide bandwidth. You're just shoveling mountains of data into the processor continuously.
Like a fire hose of data.
Exactly. But an autonomous AI agent acts much more like a human interacting with a computer.
How so?
Well, an agent might pause, quickly open a web browser to scrape a site, suddenly query a structured SQL database, pause again, and then write a burst of code.
Oh, I see. Its memory access isn't a continuous fire hose. It's incredibly bursty and highly erratic.
Precisely. LPDDR5 memory is engineered specifically to handle those rapid, unpredictable spikes in tool use without consuming massive amounts of idle power.
That makes perfect sense. They are physically tailoring the silicon to match the behavioral psychology of an AI agent.
It's extreme specialization.
But despite this monumental engineering effort, the presentation introduced a massive plot twist.
A huge one.
After detailing this incredibly vertically integrated liquid-cooled supercomputer, they announced they were integrating a completely different outside hardware architecture directly into the Vera Rubin system, a technology built by a company called Groq.
This was easily the most analytically surprising moment of the presentation.
Right. A company famous for fiercely protecting its proprietary ecosystem is actively bringing a radically different chip architecture into its flagship platform.
To understand the necessity of this alliance, we have to look at the physical enemies of semiconductor design: throughput and latency.
Let me try to break down the mechanics of those two concepts because they're constantly conflated by people.
Please do.
Throughput is the measure of total volume. Imagine a massive 50-lane highway. You can move tens of thousands of cars or massive blocks of data at the exact same time. But the traffic might be moving at a steady, moderate speed.
Right, lots of volume, but not necessarily lightning fast.
Latency, on the other hand, is the measure of ultimate speed from point A to point B. Imagine a single-lane road with no speed limit and a rocket car on it. It can only carry one piece of data, but it gets to the destination almost instantaneously.
That is a highly accurate way to visualize it. When you build a computer chip, you physically have to choose which one you are prioritizing. You can't have both optimally.
So where does Vera Rubin fall?
The Vera Rubin system, with its exaflops of compute and NVLink network, is the ultimate throughput machine. It's designed for deep, attention-heavy AI workloads.
Like if you ask an AI to read a 500-page legal brief and then summarize the core argument.
Exactly. The system needs massive throughput to hold that entire document in its active context window simultaneously.
But the architecture of a Groq chip is entirely different. It's designed to solve the latency problem.
Yes. Groq utilizes something called LP30 chips, which rely on massive amounts of on-chip SRAM memory and an architecture defined by deterministic compiler-scheduled data flow.
Okay, I know what those words mean individually, but mechanically, how does a deterministic chip function differently than a standard processor?
Think about a traditional chip like the ones in our laptops. They use non-deterministic dynamic scheduling.
Meaning?
As data moves through the chip, there are essentially traffic lights and managers constantly checking, has this data arrived yet? Is this pathway clear? Can I execute this calculation?
Lots of starts and stops.
Right. And all that constant checking and routing creates microscopic delays. It creates latency. Groq's deterministic architecture eliminates the traffic lights entirely. The software compiler analyzes the entire mathematical workload before it ever touches the physical chip.
So it knows the path in advance.
It pre-calculates the exact microsecond. Every piece of data will arrive at every logic gate.
Wow. It's like a perfectly choreographed train schedule, where every train passes through the station at the exact millisecond required, without ever needing to stop or check a signal.
Exactly. Because of that perfect physical choreography, combined with incredibly fast SRAM memory located directly next to the compute cores, the latency drops to near absolute zero.
So the Groq chips can generate the actual text tokens at blistering real-time speeds.
Yes. But because they prioritize this extreme speed, they lack the massive memory capacity required to hold a 500-page document in their context window.
Which perfectly explains the alliance. I was trying to map this dual architecture onto something familiar, and it maps almost perfectly onto human neuroanatomy.
How so?
It's as if they are actively splitting the AI's physical brain into two highly specialized hemispheres. The Vera Rubin system is the deep-thinking prefrontal cortex. It handles the massive context, the heavy memory retrieval, the deep, slow understanding of the complex prompt.
Right, the heavy lifting.
But the Groq architecture acts as the motor cortex. The motor cortex doesn't need to hold the entire philosophical weight of the thought. It just receives the electrical signal from the prefrontal cortex and physically fires the muscles, or in this case, fires off the tokens, at lightning speed.
The analogy holds up brilliantly. In the industry, this architecture is called disaggregated inference. The system fundamentally decouples the thinking phase from the generating phase.
But how do they talk to each other so fast?
To make these two disparate systems act as a cohesive brain, they introduced a new layer of operating software called Dynamo.
Dynamo, so that's like the spinal cord.
Exactly. It takes the user's prompt, routes the deep contextual work to Vera Rubin, and the millisecond the contextual math is solved, Dynamo dynamically hands the execution off to the Groq chips to physically blast out the tokens.
And the mathematical result of perfectly marrying the ultimate throughput machine with the ultimate latency machine.
The presentation stated that by utilizing this extreme co-design, total token generation speeds jump an astonishing 350 times compared to architectures from just 2 years ago.
350 times faster, all while remaining strictly inside that 1 gigawatt power ceiling we discussed earlier.
It represents a monumental triumph over physical bottlenecks.
It really does.
However, you cannot take a liquid-cooled, dual-brained, massively parallel supercomputer system and simply wheel it into a corporate basement.
No, definitely not.
The physical demands of this hardware require a total reimagining of the buildings that house them.
Which takes us out of the microscopic world of silicon design and into macro-scale construction. The presentation detailed an entirely different layer of software called NVIDIA DSX, designed to simulate physical reality through the creation of digital twins.
Right. If a corporation is preparing to invest billions of dollars to build a 1 gigawatt token factory from the ground up, the financial margins for physical error are quite literally non-existent.
You can't just guess and hope it works?
No, you cannot pour thousands of tons of concrete, install the exaflop server racks, power on the system, and then discover that the ambient air conditioning flow is missing the middle servers by 3 inches, causing them to thermally throttle.
That would be a billion-dollar mistake.
DSX is an engineering platform built within the Omniverse, which is a highly advanced virtual environment. Here, architects construct the entire gigawatt AI factory as a perfect, mathematically accurate digital twin before a single physical shovel hits the dirt.
I have to play the skeptic here, because this sounds like an exorbitant level of over-engineering. I mean, why go through the massive computational expense of simulating the fluid dynamics of air conditioning, the exact gauge of the plumbing, and the precise layout of every data cable in a virtual 3D world just to run software? Haven't we been building massive industrial facilities using standard two-dimensional CAD blueprints for decades?
We have, but standard blueprints only show you spatial geometry. They do not simulate active thermodynamics under computational stress.
Ah, okay.
DSX doesn't just show where the servers sit. It simulates how heat will physically radiate off a specific Vera Rubin rack when the system is processing a massive batch of unstructured video data versus a batch of structured SQL data.
Because the thermal output actually changes based on the software workload.
Exactly. But the most critical feature of this digital twin is a system called Max-Q, which connects the virtual simulation directly to the real-world electrical grid.
Wait, let me make sure I understand the mechanics of that. The virtual 3D simulation of the building is actively talking to the local power company.
Yes. The Max-Q system dynamically monitors the local grid's frequency and stress signals in real time. Recall our hard limit of 1 gigawatt.
Right, you can't go over it.
If the digital twin detects that the physical cooling system is running slightly inefficiently due to a drop in external humidity, and it is wasting 10 megawatts of power to cool a sector that doesn't currently need it, it instantly adjusts.
Why so fast?
Because those wasted 10 megawatts are electrons that are not being routed to the Groq chips to generate tokens.
And every wasted watt of cooling is a token that wasn't generated. A token that wasn't generated is a commodity that wasn't sold to a client. It is millions of dollars in permanently lost revenue bleeding out through inefficient air conditioning.
The economics are unforgiving. The presentation noted that at the gigawatt scale, every month of construction delay costs billions in lost token generation.
The stakes are incredibly high.
And every continuous inefficiency in the thermal dynamics is a permanent mathematical drain on your profit margin. By simulating the factory in DSX, the virtual environment ensures absolute thermodynamic perfection.
It's just wild.
And fascinatingly, once the physical building is constructed, the digital twin doesn't go away. It transitions into becoming the live, automated operating system for the physical facility.
It's an incredible chain of engineering. So if we pull back for a moment, we have solved the data problem by using vector embeddings to make all unstructured information legible to machines.
That's right.
We have bypassed the physical limits of chip design by fusing Vera Rubin's throughput with Groq's latency. We are housing these dual brain systems in perfectly simulated, thermodynamically flawless gigawatt factories.
We have the ultimate engine.
Yes. So the obvious question becomes, who is buying all the tokens this engine produces, and what are they doing with them? This leads us into what is arguably the most commercially disruptive segment of the analysis.
The software revolution.
And the death of traditional applications.
Yeah. The entire software ecosystem is about to undergo an extinction-level event. The presentation introduced OpenClaw, which they described as an open-source agent operating system.
And the metric they used to validate its impact was jarring. They stated that OpenClaw is currently being adopted by developers faster than Linux was during its explosive rise.
Adopting a new operating system faster than Linux is a tectonic shift.
But to understand why developers are swarming to OpenClaw, we need to understand the fundamental difference in how software will operate tomorrow versus how it operates today.
Right. We are looking at the transition from SaaS, software as a service, to GAAS, which is Agentic-as-a-Service.
What is the mechanical difference between those two models?
It comes down to synchronous versus asynchronous execution.
Okay, what does that mean in practice?
Well, for the last 2 decades, the SaaS model has dominated global business. A company builds a tool, say a customer relationship manager or an accounting platform, hosts it in the cloud, and charges a subscription fee.
Like Salesforce or QuickBooks.
Exactly. But a SaaS tool is entirely synchronous and passive. It requires a human being to sit at a keyboard, log in, click a button, type an entry, and wait for the tool to process it.
Right.
The software only moves when a human pushes it.
You log into Salesforce, you update a lead, you generate a report. The human is the engine, the software is just the lever.
Exactly. The shift to GAAS, or Agentic-as-a-Service, removes the human from the execution loop entirely.
Completely.
Future software companies will not sell you a passive tool to log into. They will sell you an autonomous digital agent that operates asynchronously.
So, meaning it works on its own schedule.
Right. You give the agent a high-level goal, like reconcile last quarter's European vendor invoices against our current shipping contracts, and you walk away.
Just walk away.
The agent uses OpenClaw to break that complex prompt down into sequential steps. It securely accesses your structured databases, queries your unstructured PDF vector stores, navigates external web pages, executes the math, and potentially even spawns smaller subagents to handle specific anomalies.
Okay, here is where my internal cybersecurity alarms started blaring violently during the presentation. Let's look at the reality of what we are describing here.
It's a valid concern.
We're talking about deploying highly autonomous, asynchronous software agents directly into the heart of a corporate network. These agents are reading sensitive financial ledgers, they have access to proprietary intellectual property, they can write and execute new code on the fly, and they have the capability to communicate with the outside world via email or API.
Right.
That sounds like an absolute security catastrophe. What happens if an agent hallucinates or gets manipulated by an external prompt and decides to email next quarter's unreleased earnings report to a competitor or accidentally deletes a core database?
The fear is entirely justified. And it is the single biggest hurdle to enterprise adoption of autonomous AI.
I would imagine.
You absolutely cannot have raw open source agents roaming unchaperoned through a Fortune 500 network. The presentation tackled this vulnerability directly by introducing Nemo Claw and OpenShell.
Nemo Claw, what is that?
It is the enterprise secure reference design built on top of the open source architecture.
How does Nemo Claw mechanically sandbox an agent that is designed to be autonomous?
It utilizes rigid policy guardrails and a highly complex privacy router.
A privacy router.
Yes. When a corporation adopts Nemo Claw, they integrate their existing strict IT security policies directly into the agent's fundamental operating environment. The agent operates within a mathematically confined space.
So it can't just do whatever it wants.
No. Before the agent can take any action, whether it's accessing a secure file, altering a database, or sending an external email, that proposed action must pass through the privacy router.
And what does the router do?
The router checks the action against the corporate guardrails. If the agent attempts to move sensitive financial data across an external boundary, the router instantly blocks the execution and flags it for human review.
Okay, so there is a failsafe.
It allows the enterprise to harness the massive asynchronous productivity of the agents while mathematically guaranteeing they cannot violate data compliance protocols.
It essentially hard codes a chaperone directly into the agent's prefrontal cortex.
Right.
That makes enterprise deployment viable. But what actually powers the intelligence of these agents? If I'm a corporation, I don't want to rely on one massive generalized AI model to do everything.
Which is why the presentation heavily emphasized the Neutron Coalition. The era of the monolithic, all-knowing large language model is fracturing.
Fracturing into what?
Specialized models. A model trained to write beautiful marketing copy is structurally terrible at optimizing supply chain logistics.
That makes sense.
The Neutron Coalition is a vast library of specialized open-source foundation models. They highlighted specific families. The Neutron family is specialized in advanced logical reasoning and mathematics. The Cosmos models are specialized in generating virtual world physics. The Bionio models are strictly trained for biology and molecular design.
So it's an a la carte menu of brains.
Exactly. A corporation can download these specialized open models, bring them inside their secure Nemo Claw environment, and fine-tune them using their own proprietary vectorized corporate data.
It is the ultimate democratization of enterprise intelligence. You are building highly customized, ultra-secure digital employees. But as transformative as digital agents optimizing spreadsheets and writing code might be, the endgame of artificial intelligence has never been confined to a computer screen.
No, the intelligence has to eventually bleed out into reality.
Which brings us to the final and visually most striking theme of the analysis: physical AI.
The leap from digital to physical AI is the final frontier. The presentation proudly highlighted that they had 110 distinct physical robots operating at the event.
And it wasn't just industrial robotic arms. They showcased everything from full-scale autonomous vehicles designed by BYD and Uber to advanced surgical robots, all the way down to a literal free-walking Disney animatronic of Olaf the Snowman.
It was a very diverse lineup.
But taking an AI model that functions perfectly on a server and embedding it into a physical robot walking down a crowded sidewalk is an entirely different discipline of engineering.
It is universally considered the hardest unsolved problem in artificial intelligence.
Why is that?
The fundamental roadblock with physical robots is that reality has an infinite number of unpredictable edge cases.
Right.
If you are training a digital agent to write Python code and the model hallucinates or makes a logical error, the system just generates a harmless error message. The stakes are zero.
But if you're training the neural network of a 2-ton autonomous vehicle,
and it encounters an edge case it has never seen before, say a pedestrian dropping a reflective umbrella in a rainstorm and the AI makes an error, the physical consequences are fatal.
which exposes the massive flaw in traditional machine learning. You cannot train a self-driving car the same way you train a language model. You can't just put 1 million cars on the road and let them repeatedly crash into real pedestrians, real telephone poles, and real umbrellas to teach the algorithm what a crash is.
It's ethically and financially impossible. The real world is simply too slow, too expensive, and far too dangerous for trial and error physical training.
You can never manually collect enough real-world data to cover every possible physical anomaly. So what's the solution?
The solution the presentation laid out completely bypasses the real world. The training is entirely simulation-based, utilizing advanced AI physics engines like Newton and Warp.
Operating within the Omniverse platform we discussed earlier.
Exactly.
Let's connect these pieces.
Yeah.
We're talking about using the massive Vera Rubin supercomputers to build perfectly accurate digital representations of the physical world. These aren't just video game graphics. They are rigorous mathematical simulations complete with accurate gravity, material friction, wind resistance, and thermodynamics.
Yes. And within those simulated realities, they generate endless streams of synthetic data. They drop a virtual model of a physical robot into this simulation.
And what does it do in there?
The virtual robot can attempt to walk up a flight of stairs, lose its balance, fall over, and mathematically calculate why it fell millions of times an hour.
Without breaking a single physical part.
Right. They introduce violent synthetic weather, unpredictable synthetic pedestrians, and bizarre lighting conditions. By the time the code is finalized, downloaded, and booted up inside the physical metal and plastic of the real-world robot, that machine's brain already possesses a deep foundational understanding of how physical reality operates.
The philosophical feedback loop happening here is astounding.
It really is.
We are using liquid-cooled gigawatt AI supercomputers to aggressively hallucinate perfectly accurate virtual realities. We put virtual robots inside those hallucinations so they can practice walking, so that when we finally bolt the physical hardware together in our reality, the robot instantly knows how to navigate physics. The digital universe is literally birthing and training the physical universe.
It is a profound engineering loop, and it's yielding immediate real-world results.
What kind of results?
The presentation made a bold claim that we are currently experiencing the autonomous vehicle equivalent of the massive language model breakthrough we saw a few years ago.
Like a ChatGPT moment for cars.
Exactly. They highlighted a specific new model called LPMO. Because of this massive synthetic simulation training, combined with the ability to process raw, unstructured visual data in real time, the vehicles are fundamentally changing how they operate. They aren't just reacting to stimuli.
What are they doing instead?
The LPMO model allows the car to continuously narrate its internal reasoning.
I saw the demonstration of that, and it is wild. The car isn't just silently slamming on the brakes. The AI is actually speaking to the passenger, stating, "I am decelerating because I perceive a double-parked delivery truck ahead. I recognize the pedestrian stepping out from behind it, and I am calculating the optimal trajectory to avoid both."
Right. The machine is actively reflecting on its own physical actions in real time.
Which is the absolute prerequisite for mass adoption. I mean, a human being will never surrender physical control to a 2-ton machine unless they trust it.
Transparency in the reasoning process builds that trust. We are laying the psychological groundwork for humans and physical AI to coexist in shared spaces.
Let's take a collective breath and zoom out, because the sheer volume and scale of the engineering we have explored today is almost overwhelming.
It's a lot to process.
We started our journey looking backward, analyzing how a 20-year financial gamble on parallel computing architectures inadvertently created the global install base required to ignite this revolution.
Which provided the raw compute necessary for the QDF and QVS libraries to utilize advanced vector embeddings, finally allowing AI to perceive and understand the 90% of global unstructured data that was previously locked away in the dark.
We tracked the evolution of AI through the inference inflection, moving from passive generation to active reasoning and execution, instantly creating a $1 trillion demand for physical infrastructure.
Infrastructure that must adhere to the brutal laws of thermodynamics. We explored the concept of the token factory, where a strict 1 gigawatt power ceiling forces companies to measure their survival purely in tokens generated per watt.
We analyzed the extreme co-design required to meet that metric. The creation of the 3.6 exaflop liquid-cooled Vera Rubin system, and the unexpected alliance with Groq, combining massive throughput with zero-latency deterministic routing to increase token generation by 350 times.
We saw how the immense capital risk of building these gigawatt factories necessitates the use of the Omniverse and DSX to simulate thermal dynamics and grid fluctuations in real time, ensuring absolute efficiency.
We navigated the disruptive, inevitable shift from synchronous sauce tools to asynchronous GAAS agents, powered by the OpenClaw operating system and heavily secured behind the guardrails of Nemo Claw.
And finally, we witnessed how all of this interconnected hardware and software is being leveraged to generate synthetic realities, safely training the neural networks of physical robots to operate alongside us in the real world.
The interconnectedness of this entire ecosystem is what makes this presentation a blueprint for the decade. So how do you, the listener, operationalize this? The immediate question you have to ask yourself when looking at your own business is, how will your industry pivot?
Are you currently spending capital building or selling a passive tool that a human being has to manually learn how to use?
Because if you are, the architectural clock is ticking. You need to fundamentally shift your strategic thinking toward providing an autonomous agent that executes the workflow entirely on its own. The transition from human-operated tools to independent digital agents is going to ruthlessly redefine productivity, corporate structure, and human employment itself.
It really will change everything.
Which brings me to a final, highly provocative thought that was briefly raised in the periphery of the presentation. And it is a concept I haven't been able to stop turning over in my head. They casually discussed the looming concept of an annual token budget for corporate employees.
The token budget. Yeah, that's a wild idea.
Think about the mechanical implications of that.
Huh.
We've already established that the token is the new, physically constrained global commodity. In the very near future, your compensation package, your professional value, and your sheer output might not just be defined by your base salary or your experience.
It might be mathematically defined by how many AI tokens your corporation allocates to you.
Exactly. If your company gives you a massive premium token budget to power a swarm of specialized, customized digital agents, your individual productivity is amplified 100 times over. You become a one-person enterprise.
But what happens to the global workforce when your intrinsic worth and operational capability as an employee are mathematically bottlenecked by your token budget?
What happens to the brilliant employee whose mid-sized company simply cannot afford to buy the electricity required to give them enough tokens to compete? We are moving from a labor economy to a compute economy. It is a fascinating, complex, and slightly intimidating frontier to mull over as we watch these liquid-cooled gigawatt factories begin to power on.
It's a completely new world.
Thank you so much for tuning into the Quarterly Call. For more episodes, please remember to rate and follow our show. Until next time, stay curious and stay informed.